Hello everyone, this is Robert talking to you from the Gurobi office in Berlin. My lecture today will be on non-convex quadratic optimization with Gurobi, and we will get started by looking at one particular problem type that we found interesting when working on quadratic optimization, the pooling problem. This problem showed up first in a paper from the late 70s by Haverly, and the setting you have to have in mind is that you are running an oil company and you have certain oils A, B and C as input that you want to, in the end, ship to two customers X and Y. And on top of a regular transshipment problem, you have one complication. The crude oils A, B, and C, they differ not only by a price, but also at a quality. So each crude oil comes with a certain percentage of sulfur in it. So here you see that crude oil A comes in with 3% sulfur, B with 1% and C at 2%. But the customers in the end that want to buy oil, they say my oil must have at most 2.5% sulfur, while Y says my oil that I want to buy must not exceed 1.5% of sulfur. So there must be some blending going on. You cannot ship A alone to any of these customers. And as if it's not difficult enough, you cannot just mix it at the customer side, but the crude oil traverses through a physical network where the oil streams meet and mix, and the resulting mixture has some concentration of sulfur that depends on how much of A, B, and C went into the pool. So let's look at it in more standard notation. As you might have guessed, we have as a base construct a transshipment problem. And more generally, we use as the base structure for this problem a minimum cost network flow problem, meaning that we have three sources, two targets, and there's one intermediate transshipment node here. And all the terminology from standard minimum cost network flow problems apply here. So for every arc in the network, there's a flow variable designating how much flow, how much oil in this case, goes through this arc. There's also a cost. We have to buy some crude oil here and some bounds. So if there's a physical pipeline, say, you cannot transfer an infinite amount of oil through it. And then you have flow conservation. That is in this tiny network only happening at P1. The other nodes are either sources or targets. So this is where flow comes in or goes out of the network. And now the complication that enters this problem is that we have to track the quality of the oil, which is, in this case, the percentage of sulfur. And to model this, there will be, for every node in the network, an additional flow quality variable, Wi. And I said it's a variable, but of course, we know that at the sources of the network, the quality is known, 3, 1, and 2%. We also know that at the targets of the network, this quality must not exceed a certain bound. So the sources have fixed quality from the start, the sinks have an upper bound on the quality. And now the interesting part is what happens at P1. And the most simple model you can think of is if you mix two different quality of oils. The resulting quality is just the average of the two, weighted of course by the amount you have put into them. And this is exactly expressed in this equation. So at P1 we have a quality of flow constraint that says if I go over the incoming flow for each j in the incoming node set, I get the weighted quality by the incoming flow rate, and this must match the quality of node I, in this case P1, times the sum of the flows. So this means nothing else but what I just explained. It is a linear mixture of the flow qualities. Now if you do a web search on pooling problems, what you will discover is that this is just really the basic, really the base model of pooling problems. Typical complications that you will get in addition to that is that you don't have just pools between the sources and the sinks, but also multiple pools that mix downstream even further. You can model this similarly, like the quality of flow constraint that we just saw. And another complication is that while in this example we only had one quality attribute to be satisfied, the sulfur, in reality you may have many attributes and the targets may have different demands for each of these attributes. So this is typical in pooling problems as well, as you will discover. And if you search a little bit further, the quality of flow constraint that I have shown to you, this goes often by the name the quality formulation of the pooling problem. There are other ways to formulate that, and if you will web search on the proportion formulation, you will find something else which affects the same, or you can find hybrid formulations of these two. But there's one feature that is common to these formulations. There will be quadratic constraints due to the quality of flow constraints. And what does it mean now that we have this quality of flow constraint? If we imagine there weren't any, what do we end up with? It's just a pure network flow problem. And this is just nice. It's known, polynomial complexity, integer solutions are always guaranteed as long as the input data is integer. And once you have a locally optimal solution, you know automatically it's globally optimal. But instead, now that we have these nasty quadratic constraints, the problem is NP hard. The problem may have many locally optimal solutions. Local solutions may not be globally optimal. And the feasible region, if you look at it from an abstract point of view, may have holes or maybe disconnected, all kind of nasty things happening here. And the reason is the non-convexity of these quality of flow constraints. Let's look at it more precisely. The quality of flow constraint at P1 reads this. I mean, it's obviously quadratic. We have products of Wj times Fji, and here we have products of Wi times the outgoing flow arcs. Now, a quadratic expression equal to some right-hand side. This is already, in most cases except for degenerate ones, a non-convex set. Simplest example, I think of the solution set of the equation x squared equal to 1. But here it's even worse, even if you settle for, okay, let's look at the sub-level sets, not at the equation, but look at the sub-level sets of this quadratic function, already this is non-convex. So this is really bad. Maybe that's a good time to just get some basic background things straight. So let Q be a symmetric matrix and consider the quadratic function f, which maps x to x transpose times q times x plus this linear part. And the important things to remember is f is a convex function if and only if q is positive semi-definite. It is strongly convex if and only if q is positive definite. And if q is positive semi-definite, then all sublevel sets f of x less or equal than c are convex sets. And this is of course the nice case. This is where again polynomial complexity is guaranteed. You have efficient algorithms and theory is very nice. So we need to depart this region, unfortunately. And since it's a lecture, there's one piece of homework for you. Here is some quadratic function, the simplest one I can imagine. And maybe you can determine what the matrix representation of this function is and whether it's convex or not. I didn't pick it just for the function itself, but because we will handle this object in the following slides a little bit more in detail. So if you see this constraint here, x times y equal to z, this is sometimes called a bilinear constraint. And we'll talk about that a lot in the next slides. Just for the wording, bilinear, what's bilinear here? I mean, it's just the product x and y. Obviously, the function f of x and y equal to x times y is linear in the first input and linear in the second input. Of course, it's not a linear function, but it's a bilinear function here and here. All right, so let's switch gears and let me explain a little bit how Gurobi handles non-convex quadratic functions. Just to get the terminology right, a mixed integer quadratically constrained problem, MIQCP, is defined by a quadratic objective function and a number of quadratic constraints. In addition, of course, you may have integer requirements on some of the variables. In all of this, we assume that Q, K are symmetric matrices. And whenever a matrix Q has a non-zero element, what this means, if you write it down term by term, is that you get one mixed term if it's off diagonal or a square term if it's on the diagonal of Q in either the constraints or in the objective. Now, if all the Q matrices here are semi-definite, then we're again in the comfort zone, meaning that, for example, if we can just skip the integrality from the QCP relaxation, the resulting problem is already convex. So this is something Gurobi has been able to solve for a long time. And for the latest release, we worked a little bit on handling the case where these Q matrices give rise to non-convex quadratic constraints. Let's review what the standard technique in Gurobi for convex functions is, and then let's see why it doesn't work for non-convex. So previously, before Gurobi 9, it was required that all the Q matrices are positive semi-definite, because this gives you the convexity. Except for a few special cases, we can skip over that. You see, this is another function which, regarded as a function, is non-convex, but actually the level sets, which happen to be disks, are convex. Now, what do we do with non-convexity? Before version 9, there were two types of non-convexity that we treat, which are integer variables and special ordered sets. What we added for 9 is specifically working by linear constraints. And these are treated exactly by the same framework as integer and special ordered sets, namely by cutting planes and by branching rules. And now you may wonder, okay, we support bilinear constraints, but what about this non-convex Q? Well, the reason is that you can always translate a non-convex quadratic constraints into a set of bilinear constraints plus a linear constraint. So the transformation is really simple. You look at the original constraint, you look at each quadratic term, 1, 2, 3, 4, 5, 6 there are, and now for each term you add one auxiliary variable that must match the quadratic term. So z11 must be equal to x1 squared, this is this portion. We have z12, which must be equal to x1 times x2, this is this term, and so forth for everything else. And now if you substitute the quadratic terms by the auxiliary variables, you end up with one linear constraint here. Okay, so it means all you need to be able, technically, to treat is bilinear constraints like this. So the general form of a bilinear constraint that we support is some linear portion plus scalar times the product of two variables, less or equal to some right-hand side constant. And so the notation and techniques become a lot easier if we look at the square case first. So here x is equal to y. If this happens to be convex, like in this example, minus c plus x squared less or equal than 0, then what we will do is we will ignore the constraint and solve the LP relaxation. Then afterwards, we will add tangent cuts to it to guarantee feasibility of the solution. So how does it work? Imagine we solve the LP relaxation, ignoring the constraint. We may get some optimal solution of the relaxation sitting outside the feasible domain of the quadratic constraint. So what we will do is we will add a cutting plane that cuts the solution off. Now we resolve the relaxation, the solution may now be here, we iterate a few times, and hopefully after a small number of added tangent cuts, the LP relaxation will be close enough to the feasible region of the quadratic constraint so that we can account it as feasible. So that's the easy part, and that's what we've done for a long time. Now for the simplest non-convex quadratic constraint, minus c squared less or equal than 0, this won't work. Because there is no, in general, there is no linear hyperplane that we could add to the problem that cuts off the LP relaxation while at the same time leaving the feasible region of the constraint uncut. So this won't work. And now we go into a different technique. We say, okay, then instead let's branch on the feasible domain of the variable x. So in the standard branch and bound framework, this means we would say add two new nodes, one with the additional restriction x must be less or equal to 0 and the other x must be greater or equal to 0. And then in the child nodes, now the point defined by the LP relaxation of the global problem can be separated away from the feasible region of the convex hull of the feasible region of the quadratic constraint when using the local bounds for x, and same for the other node. Okay, so bottom line is, branching does the trick here. Now let's look at the mixed product case. And now the notation gets a little bit more complicated, and the pictures get a little bit more complicated, but it's still pretty easy to see what's going on. So this is the feasible region of the bilinear constraint minus z plus x times y equals to 0. And what we do here is we add to the LP relaxation lower and upper envelopes of the surface. So if we add all these constraints, we get a linear relaxation of the problem, where of course, which includes of course a lot of infeasible points for this quadratic equation. But the nice thing here is that these hyperplanes, they are defined in terms of the bounds of the entering variables x and y. And now, as we move along in the branch and bound tree, we divide the bounds of x and y further and further into smaller intervals. These envelopes will become tighter and tighter for the feasible region of the quadratic constraint. So this works well with the intent of branching, bringing the linear relaxation closer and closer to the feasibility region of the nonlinear problem. Okay, so and now looking a bit at data structures and techniques, what happens under the hood. The coefficients and right-hand sides of the envelope defining equations, they depend on the local bounds. So whenever we branch on the domain of a variable in a quadratic constraint, we need to modify the LP coefficients in the basis matrix that is maintained throughout the branch and bound nodes. I mean, this is a departure from the comfort zone of branch and bound. If you think about branching for integrality, you just modify the bound of a variable. So whatever you modify, the optimal basis at a given branch and bound node remains the basis. But here we now have one more complication. We change coefficients in the basis matrix, and there is no a priori guarantee that after such a change the basis is still a basis, so it could become singular. In the worst case, this means for us we may need to throw the basis away. Maybe we can repair it by some tricks, but this is again not guaranteed, and start over from scratch. And just to mention it, something that we did not pursue, which is an alternative that you could think of. Instead of modifying the envelope equations, you could just add the tighter equations as you go down in the branch and bound tree. So at every node at a given depth, you get possibly tighter relaxations, and there you would not modify the pre-existing envelope equations, but add new ones, which of course means the more global, so up the tree constraints will become slack, but you don't run, and you add other equations, so you don't run into the problem of modifying any equations of the basis matrix. But the disadvantage then is that if you need to have the ability to add rows to the LP relaxation during branch and bound, you need quite dynamic data structures that support this operation. And this is also quite difficult to get right and efficient. So that's not what we do. We opted for this technique here. And now let's talk a little bit about branching. So we have three non-convexities: integrality, special ordered set, and bilinear constraints. And the first thing we do is we branch on fractional integer variables until there are no more, and then we only then we start looking at bilinear constraints. And there are two aspects now that you need to consider. One is which variable you pick for branching, and the other is what is a good branching value. So let's talk about the first one. What you want to achieve with branching is that the bilinear constraints that are violated the most get reduced in violation, and the other is that you reduce the volume of the envelope around the quadratic constraint. Because these two define, after all, the success of a branching variable. The better you divide the polyhedron, the closer you get with the envelope to the true feasible region, and the fewer largely violated bilinear constraints you have, the closer you move to feasibility. So these two constitute somehow branching rules. And what we also use is, which is well known for the MILP techniques, we use shadow costs for X and Y for selection. Well, then you need to decide where to split the domain of a variable. And this problem you don't have as much if you look at integrality constraints. I mean, if you have an integer variable sitting at 3.5, I mean, you typically, unless you know something better, you would say, okay, one node is at most 3 and the other is at least 4. And now here, because the domains of X and Y are continuous, you have to spend a little bit more thought. One way is to choose points that really try to minimize the sum of the volume of the resulting envelopes. And the other is it's difficult to pinpoint, but you have to avoid certain pitfalls. If you say, oh, I have a domain 0 and infinity, and a good branching value is now 1 billion. That's not going to work. In that moment, you have decided to enter a huge numerical quantity into the logic that does simplex pricing and solving, and this will inevitably result into numerical problems. And there's other aspects that if you choose the branching values too close to previously branched values on, you may just generate a huge number of nodes in a very deep dive. So that's something else to watch out. And beyond branching, there's the second key technology for nonconvexity, which we use already for integrality constraints and SOS constraints, which are cutting planes. And what we did for version 9 is we added or adapted existing cutting planes to help us with bilinear constraints. So one class is the RLT cuts. This comes from reformulation linearization technique. So if you don't know what it is, in short it is, you take any constraint, multiply it by some variable, and then you linearize again the product terms. This gives you a linear inequality, and if you were lucky and you picked the right rows to play with and the row variable, the right variable to multiply through, you will find that this constraint is often violated then by the current LP relaxation. So you can add it as a cutting plane. And this is most helpful for bilinear programs, because you already have linear auxiliary variable for all the product terms, but you can do some tricks, and actually you can use it also for convex MIQCPs and even MILPs. Another class of cuts which is interesting are derived from facet defining inequalities for the Boolean quadratic polytope. This we evaluated and found quite useful, but we only implemented it for the smallest possible clique size, so cliques of size 3. And there's one more interesting class of cuts, which is not in 9.0. These cuts take a more global view on these auxiliary variables. So just in short, if you model your auxiliary variables z like this, so the matrix of auxiliary variables z is equal to the outer product of the actual variables x times x transpose. This is of course a valid equality, because that's how you define your auxiliary variable. So you can relax it, but you do not relax it element-wise, but you relax it in the Löwner ordering. So you end up with a constraint that z minus x times x transpose must be positive semi-definite. And now the game is find a vector that shows that this matrix here is not positive semi-definite and use it for separation. So we will look into this, and this may come on in the future. And that's pretty much all I have to say today. So thank you very much.